David Smith here with another Flip Classroom math lesson. 3 tips before we start. First, you can adjust the playback speed to suit your ability to consume the video. Second, you can pause the video at any point to catch up with your notes or jot down questions. Third, you can turn on the captions and read my words on the screen. Today's lesson covers the distance formula. And just like with the midpoint that we did last time, we're going to do this in 2 dimensions and then in 3 dimensions. My guess is you've probably already done or used the distance formula in 2D, so maybe the 3D part's new. Fortunately, it's not that much more complicated. Very much like how the midpoint formula got more complicated in 3 dimensions. Very similar. Okay, so let's look at a definition here. The 2D distance formula for 2 points, x1, y1, x2, y2, the distance between them is d for distance. It's the square root of x2 minus x1 squared plus y2 minus y1 squared. This is basically a big plug-in problem. You solve the parentheses, you square them, you add them, you take the square root, and you have your distance. So let's take a look at an IB-style problem that you might get and have to use the distance formula to solve. So let's look at that. So here's my scenario. This is a river. Put some river waves in there. And we have a bridge crossing the river. Okay? Now this is all mapped for you on the coordinate plane. And that's important for using the distance formula because you notice we have x and y coordinates in here. We're going to need to know those to calculate the distance. So take a look at that diagram, think real hard, and see if you can figure out how to use the distance formula to find out how long is the bridge. Okay, let's see how you did. Bridge length. Here's what we're calculating. Now, this is what I like to do. I'll come over here and I'll go x1, y1, x2, y2. That way, there's no confusion for the plug-in step. You know exactly what you have to do. So, let's do this. Square root of, now x2 minus x1 squared. That's going to be 60 minus 20 squared. So I'm just going to do a straight plug-in step. 60 minus 20 squared plus, now y2 minus y1 is going to be 30 minus 40 squared. 30 minus 40 squared. Close my root. Now there's my plug-in step. I urge you to resist doing math on the plug-in step. Notice how, I can subtract 20 from 60 and get 40 really easily, but I just want to show that I know exactly what I'm doing right on my plug-in step. You want to do that. Okay, now let's simplify this down a little bit. 60 minus 20 is 40. Squared is 1600. So that's 1600 plus, now 30 minus 40 is negative 10. Squared is going to be 100. So then we have the root of 1700, and you can get out your calculator and get that answer. Okay, so I punched in my calculator and I got 41.2. Since this is a word problem, let's do the reasonableness test. Is this answer reasonable? And I think it is because this bridge has to be 41 meters, let's say meters, has to be 41 meters long, and that makes kind of sense because it's going from 20 to 60, roughly, so that answer is in the right ballpark. And I do need to have units, so let's call it meters. In fact, my graph should have meters right there and meters right there. Okay? Okay, let's move on to the 3D distance formula. A little more complicated, but pretty much the same idea. So what we have is for any 2 points, x1, y1, z1, remember 3D space has 3 coordinates, x, y, and up. So 2 points, x1, y1, z1, and x2, y2, z2, the distance is, check this out. This is the same as the 2D distance formula, you just have another term for your z-axis. Otherwise, it's the same type of a formula. Okay, so we're going to bounce around on this problem for a little while. What I've drawn here is a cuboid on a 3D coordinate plane. Remember we have x, y, and z is your vertical axis. And then I've drawn my cuboid in here, and I've labeled my axes, my corners. So I have A, B, C, D around there, and then I have R, Q, F, and O around there. So, and then notice how we've given you the coordinates for one of the points, point A. It's 2, 3, 4. So that's 2 out on the x-axis, 3 along on the y-axis, and 4 up on the z-axis. So remember, 3D space is a little bit more complicated than 2D space. So here's your first question. What are the coordinates of Q, F, O, and R? And you might look at that right now and go, what? How the heck could I figure that out? There's a key thing that helps you do that. This back bottom corner of our cuboid is on the point 0, 0. So everything else goes out from there, and you can figure everything out. So I want to do 0, 0 first, or O. Point O is 0, 0, 0. So O is 0, 0, 0. That's great. So now let's take a look at R. So R is scooting along the x-axis the same amount as A has come out from the back. So you kind of have to visualize that in 3D. But point A is 2 units along the x-axis, and it's going to be the same distance as point R. But R is not going along the y, and it's not going up on the z. So R equals 2, 0, 0. Okay? Now, it can be a little confusing, but you can get the hang of it if you keep working it. Let's do Q. We know what R is, so now we can just go up to Q. So Q is going to be, so check it out. The x-coordinate of Q is also 2, because we've come out the x-axis by 2. But now we've gone up on the z-axis. How much? We've gone up the same amount A is on the z-axis, and that's 4. So this point is going to be 2, 0, 4. And it's 0 in the y, because here we haven't yet gone along the y-axis. So the y-coordinate here is 0. Now our last one, let's see, we did O, R, and Q. We've got F. I'm going to squeeze F in right up here. Now F, this one's interesting. It's not gone along the x-axis, so that's a 0. It hasn't gone along the y-axis, so that's also a 0. It's just gone up the z-axis by the same amount that A has come up the z-axis. So F is going to be 0, 0, 4. Now, figuring out points like that is going to be essential to working some of the problems. So that's why I took a little extra time with that. Now, here's an IB-style word problem question. So let's read it off, and then I'm going to see what you can come up with. What is the max length for a garden tool that still fits in the shed? And let me give you a little context here. You might have noticed that I wrote up here cuboid garden shed, right up here. So yeah, it looks just like a box on a diagram. But let's pretend that this is a shed where you can store garden tools like rakes and hoes and shovels and all the things you need to work on your garden. So what they want to know is what's the longest tool that we can store in that shed? The max length. So pause the video and think about that for a minute. Maybe just come to a qualitative idea about how that would work and what that would be on the diagram. What distance would that be? Okay, let's take a look. So the longest tool would go in one corner, and it would go all the way through the middle of the cuboid of the shed, and it would hit the opposite corner on the top side. So that's the longest possible tool. So what we need to calculate is the length of a diagonal of a cuboid or of a rectangular box. Okay, so we just need to calculate the length from A to O. Now here's the thing. We could calculate there's like 4 different diagonals that can be drawn. There's A to O, there's D to F, there's R to B, and there's C to Q. Those are all diagonals of our rectangular box, and they're all the same length. So let's pick the one that makes it the easiest. Pause the video and see if you can figure out which one that might be. Okay, if you said, well, of course, let's use this one, you're right, because point O is 0, 0, 0. And so that means we plug into our 3D distance formula, one of these two numbers in each of these little binomials is going to be 0. So that just makes it a little bit more simple. Okay, so now we know that we're calculating the distance of a line that goes from 0, 0, 0 to point A, which is 2, 3, 4. So go ahead and pause the video and do a plug-in step with your distance formula. Action. Okay, so let's see how you did. I did x2 minus x1, that's 2 minus 0 squared, and here's my x1, that's 0, and I labeled my points, x1, y1, z1, x2, y2, z2. And I finished plugging it in. Y2 is 0 minus y1, which is, y2 is 3 minus y1, which is 0, and z2 is 4, and z1 is 0. So there's your plug-in step. Go ahead and pause the video and do the calculation if you haven't already. Okay, let's see how you did. My answer is 5.39 to 3 sig figs. Let's do the reasonableness test, okay? So take a look at your box. You notice this dimension is 2, this dimension is 3, and that dimension is 4. So if a diagonal of the box is 5.39, that makes sense. It's within the realm of possibility. If we got 1, that would be bad. If we got 20, that would be bad. Okay, one last little problem. This one I think you can just get without me doing anything. Find the height, RQ, of the garden shed. Pause the video and figure that out. Okay, there's no calculation here. You can just tell from the diagram. So I'm going to change one word. List. Okay? List is an IB term that you should pay attention to. Like list and state mean that you should be able to just pull the information from the problem. Find indicates that you need to do a calculation. Now, we could calculate the height of the box, but we can list it because the information's right there. So, see if you can do that. Okay, check it out. Let's see how you did. RQ is right there. Okay? So now that I've pointed out RQ, see if you can figure out what the height is. Okay, check it out. RQ is just the distance we've gone up the z-axis. That's all it is. It's the height of the box, which is what they're saying. So that distance is right here. That's the 4. Our z-coordinate is 4 up. Remember, this point here is 4 up from the bottom, from the origin. So we've come 4 up to A. Q is the same height as A, so RQ is 4. There you have it. Now that you've watched the video, jot down a few extra notes or questions for our next class. You can also re-watch portions of the video that didn't go in so well the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.